Chapter 2, Exercise 24. Hints. Use the given hint. Solution. If the set X is finite, then it is trivially separable. Thus, we assume that X is infinite. Suppose that there exists delta greater than 0 such that for every finite subset, A subset of X, the union here, that is, X cannot be covered by a finite number of neighborhoods of radius delta. We construct a sequence here in X inductively as follows. Choose any x1 element of X. Since this, there exists this, so that this. Suppose x1 up to xn has been chosen such that this for all distinct ij in this. Since this, there exists a point this. By construction, this for all I equals 1, 2, and so on up to n. Continuing this process, we obtain an infinite sequence here of points in X satisfying this for all distinct integers I and j. Define the set E equaling this. Since all xi are distinct, E is infinite. By the assumption of the exercise, E has a limit point y element of E prime. Consider the neighborhood n delta over 2 of y, which must contain infinitely many points of E, theorem 220. In particular, there exist distinct indices I, j such that this. Then, delta less than or equal to the following, which is a contradiction. This proves that our initial assumption was false. For every delta greater than 0, there exists a finite subset A subset of X such that X equals this. Now, for each positive integer n, consider delta equals 1 over n. There exists a finite set an subset of X such that X equals this. Define D equaling this. Since D is a countable union of finite sets, it is at most countable by the corollary to theorem 212. To show that D is dense in X, let y element of X and I greater than 0. By the Archimedean property, there exists an integer n such that 1 over n less than r. Since X equals this, there exists X element of an subset of D such that this. Hence, every neighborhood of y contains a point of D, which implies D bar equals X. Thus, D is an at most countable dense subset of X, proving that X is separable. Comments. A metric space is called totally bounded if, for every delta greater than 0, it can be covered by finitely many neighborhoods of radius delta. In solving the exercise, we established the following two facts. 1. If every infinite subset of a metric space has a limit point, then the space is totally bounded. 2. Every totally bounded metric space is separable. Let X be a totally bounded metric space. For each delta greater than 0, the space X can be covered by finitely many neighborhoods of radius delta. Denote by L delta the minimal number of such neighborhoods needed to cover X. The sequence of values, set of L delta, is closely related to the concept of metric entropy, which is widely used in various applications to quantify the complexity of a metric space. Thanks for watching.